This video will discuss the concept of bond order in homonuclear diatomic molecules. So if we look at our electron, our molecular orbital energy diagrams of our homonuclear diatomics, I've got 5 of them drawn here. So I've got H2, helium-2, carbon-2, F2, and O2 plus, and oxygen-2 cation. So we know that H2, we have this kind of idea from general chemistry that there's a sigma bond going on there, and that helium-2 doesn't really prefer to bond. And the same kind of idea that we think of fluorine-2 as being a single sigma bond. So where do we actually quantitatively get that from? So we get that from a concept called bond order. So the bond order is going to be determined by 1/2 times the quantity, number of electrons in bonding molecular orbitals, minus the number of electrons in antibonding molecular orbitals. So each electron in a bonding MO is going to contribute to half of a chemical bond. Each electron in an antibonding molecular orbital is going to contribute minus 1/2 to the number of bonds. So using this formula, we see that H2 has 2 electrons in 1 sigma G, so that's 2 bonding and 0 elsewhere. So 1/2 times 2 minus 0 gives us 1 bond. Additionally, these electrons are in a sigma orbital, so it forms a sigma bond. For helium-2, we have 2 electrons in 1 sigma G, 2 bonding, 2 electrons in 1 sigma U star, antibonding. 1/2 times 2 minus 2 gives us 0, or 0 bonds. So that idea that helium-2 doesn't really bond, that noble gases prefer to be by themselves, is backed up by this calculation because it says that there's a net of 0 bonds in helium-2. All right, carbon-2, we can do the same kind of thing. 1 sigma G, 2 sigma G, 1 pi U twice, 8 electrons in bonding orbitals. 1 sigma U star, 2 sigma U star, 4 electrons in antibonding orbitals. 1/2 times 8 minus 4 is 2 bonds. Notice that the sigmas are equally canceled by sigma stars, but all of the pi's remain. So this C2, we would say it has 2 pi bonds. For fluorine-2, F2, diatomic fluorine, we do a similar thing. 1 sigma G, 2 sigma G, 3 sigma G, and 2 1 pi U's. There are 10 electrons in bonding orbitals for F2. 1 sigma U star, 2 sigma U star, and 2 in 1 pi G star. There are 8 electrons in antibonding orbitals for F2. 1/2 times 10 minus 8 gives us 1 bond. The pi's are canceled out. All the pi's are canceled out by pi stars. 3 sets of sigmas, but only 2 sets of sigma stars. So in fact, this comes from a net bonding from the 3 sigma G orbital. So this we would label as 1 sigma bond. So far, so good. So the last example is O2 plus. So the professors love these types of diagrams. They love questions about them. So you 100% should memorize these diagrams, the formula for bond order, what these labels are, all that stuff. But really the only gotcha they can do is to throw in anions or cations. So these are all fairly straightforward because the number of electrons are always going to be even. But for an anion or a cation, the number is going to be odd. So O2 plus, I build the same diagram that I would have for O2, but the difference is I have a cation, so I have to take 1 electron away. So instead of having 16 total electrons, I have 15 to add up to my orbitals. If I had O2 minus, I would have added an extra electron. I would have had 17 instead of 16. So cation or anion just depends on adding or subtracting an electron to make the math work. All right, O2 plus, same thing. 1 sigma G, 2 sigma G, 3 sigma G, 2 1 pi U's, 10 bonding electrons. 1 sigma U star, 2 sigma U star, and 1 electron in 1 pi G star, so 5 antibonding electrons. 1/2 times 10 minus 5 gives us a bond order of 2.5. So taking away that electron took away an electron from an antibonding orbital. So O2 plus actually has a higher bond order than O2 because we would have put that last electron in an antibonding orbital. So half bond orders are allowed in this type of bond order calculation. And if you calculate the numbers of sigmas and pi's, you'll see that we have 6 sigma bonding and 4 sigma antibonding, giving us 1 net sigma bond. And we have 4 pi bonding and 1 pi antibonding, giving us 3 halves, or a net of 1.5 pi bonds for O2+.